already. I think I should start already, 11:30. So my name is Xin Wang. I think they already introduced me. And today, first of all, I try to thanks very much. The conference give me a chance to introduce my lab research. Today, my topic is melatonin and NAS offer neuroprotection in experimental models of ischemia stroke. Yeah. And I try to introduce some background sentence. So here, stroke is one of the leader case of death worldwide. According to the World Stroke Organization, every 6 seconds, someone somewhere will be died by stroke. And 1 in 6 people will at some time have a stroke during the lifetime. So I think this is a kind of serious situation. If you're counting, 1, 2, 3, 4, 5, 6 seconds, one person died by stroke. And if you're counting another 1, 2, 3, 4, 5, 6 seconds, another person died. It's very, very quick. It's very, very quick. It sounds like a so serious situation here. And we don't have very good drug. We don't have very good drug to treat stroke patient, except TPA, but as Dr. Harvard talked, only very short treatment window, very short. So I think the developing new drug for neuroprotection for stroke patients urgently needed. And the long term my lab name is Neuroprotective Drug Discovery Laboratory. Our long term aims to find new neuroprotective drugs for cure adult ischemia stroke. We're also working with neonatal model, neonatal hypoxia ischemia, we call HI, brain injury model, HIE. So here's 3 types of stroke, ischemia stroke, and ICH, SCH. Today we focus ischemia stroke. Also, Harvard already talked, just momentarily, so 85% about all stroke is ischemia stroke. So this is our focus. Okay. So this is one figures come from one review paper about 4 years ago from my lab. So we try to summarize CNS agents for ischemia stroke and all these agents with neuroprotection ability, and we target different mechanisms. Also, we're talking about ischemia stroke, we're talking about Huntington, ALS, Parkinson, Alzheimer. So neurological diseases are complicated mechanism. So we try to get things easily to understand. So for ischemia stroke, we try to divide the several kind of mechanism. This one is antioxidants. So shows oxidative stress, this mechanism. And this is anti-apoptosis. So drug will be, this bunch of drug will be anti-apoptosis in this territory. And some drug for the anti-inflammation territory. So this is anti-excitosity. And also hormone therapy. Here we're talking about cocktail combination therapy, and one drug have more function. For example, melatonin. This drug is anti-apoptosis, also is antioxidant. So several functions put together, one single drug. Okay, now we're talking about melatonin. Melatonin, I think people know it's not like a new drug. So normally people use this one for to be sleeping pill. I know someone this time come for this meeting. Someone come from United States, maybe just the early morning right now there. So you come here I'm still sleepy, something like that. And Chinese from China here also different timing. You jet lag. So melatonin is a drug for the sleeping pill, drug lag. And we can buy easily from CVS, Walgreens from the United States, I know. So it's easy to buy. And this drug not only have function for sleeping pill, but also have neuroprotection ability in bunch of neurological disease, including stroke. like today's topic, like, okay, adult ischemia stroke, newborn HI, brain injury, also for ALS, for Huntington, for Alzheimer's disease, Parkinson. So my lab working for this drug for many years. We have a bunch of publication already. And this is one figure that shows melatonin working to decrease damage in the MCO stroke, ischemia stroke model, animal mice, this is mice. So here you can say, this is the TTC staining, as I have already talked, so I don't talk so much detail. So we use similar technique for TTC staining. And here we try to document one thing as in fraction volume. You see the white colors. This the volume we try to document how much quantitatively, how much change. And another we try to say how about situation, neurological score change. If you put drug without drug, see any difference. So I also try to highlight this ischemia stroke area, at least like a focus, majorly focus in the cortex area, hippocampus area, striatal. So this figure shows melatonin treated either pre-treatment or post-treatment. Protect brain-like damage for MCO model. We give significant difference. So the drug works. So this paper published like 6 years ago. And now I'm talking about in vivo already shows animal data. Now it shows cellular data, in vitro data. As I said, like primary, as I said, cortical neuronal or cortical area is important for stroke. So this we did primary cortical neuronal cells. We call PCN cells. So PCN cells induced by apoptotic inducer like NMDA, H2O2, OGD, like we have a bunch of apoptotic inducer. And then we try to see how much killing. We use LDH assay to quantitatively document. So this is like a cell itself, this is cells. Here is a cell with NMDA treatment. You can see almost 2 times more cell killing. Comparison is white column. This is more killing in the NMDA treatment cells. All blue colors with drug treated, melatonin treated drug, the cells, different dose. You can see if you put melatonin here, you have less killing. And if you put here like maximum or optimum condition, like 10 micromolar or 30 micromolar, you have maximum protection. And all red colors, we put this antagonist called luluzone. Here's the situation. So we have melatonin is agonist for melatonin receptor. So we have receptor there. We have agonist. We have antagonist. Like they fighting each other for the binding side. So some leucine blocked melatonin function. This is in PCN. And next one is also PCN cells, but by OGD treatment, by oxygen glucose deviation. This mimical stroke model in the animal models. And this one we try to say PI chain, test melatonin in the PI chain primary hippocampus neuronal cell culture. We get similar things. We use H2O2 to be inducer. And this is we did for ST14A striatal cell line, the striatal specific cells. Also, we get similar things. With melatonin, we get protection. With leucine, block the protection. But we use MTS assay, so you can see the way just like opposite. And we also get IC50 for this drug is 15.5 micromolar, and maximum protections 62.7%. This we use another assay. We use LDH already. We use MTS assay already. So now we use tunnel assay to check apoptotic the situation. So here is PCN cells. We use H2O2 treated to be a apoptotic inducer. Then you see here is tunnel staining cells. Control cells just like several cells, green. So several cells, apoptotic cells. If you put H2O2 there, more killing. A lot of cells already get killed. So this is apoptotic cells. We have more number cell dies. And put melatonin, get less apoptotic cells. If you give leucine together with H2O2, then with melatonin, you say, okay, so killing back. So again, shows the similar conclusion. Yeah. Okay, so now we see this sounds like a universal, not only PCN, not only PHN. This like every cells we test is like this is conclusion. So we did molecular Dunkling analyze to try to see the binding situation. As you can see here, this red and green, this is melatonin receptor 1A structure called Rabin presentation structure. And this is MT1 structure, protein, big protein structure. And we put small molecular melatonin here, insert into the let's say this is big protein. You have small melatonin. Insert in the structure. See what happened for binding. And this one, the lower part is this small molecular non-melatonin is leucine down to see who is binding strong, who is binding less. And we get conclusion is, okay, we find one strong pi-pi stack interaction, and the band of leucine down causes the shift of hydrobond contribution to leucine down's strong binding with MT1. So this antagonist more strong binding with protein. So this logically then block to melatonin's neuroprotection function. Okay, so now we say, is melatonin receptor really involved to the neuroprotection effect the agonist MT1 like melatonin or others? So in the stroke models, and so next we focus MT1, this protein. So MT1, we did Western blot for PCN for striatal cells. We use H2O2 or temperature shift to be inducer. Then we say, if you put cells in the bad condition, I call like a apoptotic condition, this protein gone or decrease. See this band comparison with control. It's gone, yeah. And also here get less, here almost gone. So from cell culture, you say melatonin receptor MT1 is lost or reduced in apoptotic culture cells. And if you put melatonin here, the melatonin receptor 1 is agonist. So the bind back comparison, this one more than this, this one more than this, this one more than this. This is cell culture situation. This is animal. MCO model. If you get MCO brain, MT1 almost gone. But if you put MCO mice with melatonin treated, kind of back, MT1 kind of back, so recovery here. And so we see several results shows MT1 really important. Then we want to get, okay, how about knock out this protein? If we knock out this receptor from cells, what will happen? Now we knock out the cells by siRNA assay. We use, we purchased four, actually we did four MT1 siRNA, but 2 perfectly work, 1 and 2 perfectly work, target MT1 explosion in the cells. We did transiently transfection, use the agent from Quigen. So here you can see this is messenger RNA level. This is cell itself without knockout. You have here the number here about seven. But if you knock out this RNA and you only have about 2 here, another one also very nice. From protein, even better. Well, but by Western blot, you see here almost reduced, almost gone this protein. And so here shows we did successfully we knock out. Okay, successfully we knock out this protein in culture cells. And this data shows after we reduce this, we knock out MT1 from cells. Is this cell still working with melatonin? How about response with melatonin? Let's see here. If you use H2O2, we kill cells. And we use melatonin to get protection. These cells without any knockout. But here's the cells already get knocked out. So melatonin is still working? Answer is not, because you get this receptor out. So this important receptor, if you put drug, and drug mechanism targets some receptor out, we don't have receptor, so your drug not working. So this is the data shows our hypothesis works. Okay, and this one is another experiment show how about this receptor itself. Is this receptor also have ability for neuroprotection? So we did overexpression by transcendental transfection by Lipton 2000. So we say, okay, so this is empty vector DNA 3.1 with GFP for easy to say and microscopy. And here we have also this one with temperature shift, like a apoptotic killing treatment. So we have less MT1, shows less cell density, almost half cell dying. And we put this one, with MT1 overexpression plasmid there. We get more cells survival. So this bunch of cells because MT1 overexpression. So get more cell viability is higher. So we think MT1 have ability to be protection. And now I try to say, I already talked, okay, cellular model for ischemia stroke, adult ischemia stroke, animal model I'm saying, oh, now we're talking about neonatal model. My lab have neonatal model for pups, for comparison with humans, just like newborn like ICO or newborn place, have new baby. So here is we show melatonin decrease damage from like newborn HI brain injury. We use Fourier G staining to show apoptotic cells, and here the green cells shows cells not good cells, and also this one is just like pops, small pops, very tiny. The pops treated by HI, by hypoxia ischemia treatment. Then after that you get section of brain section. You see hippocampus already have damage, very strong damage, cortex damage. But if you put melatonin, it's pretty good. Let's have what was beginning was not believe it was so good like this, but this one, but if you put melatonin, only some cell get killing, like very good protection. Here is neurological scar. Also melatonin have significant protection for scar. And here is knockout MT1 story. My lab have MT1 knockout colon. It's mice. So we have adult mice. We have pups, small pups. One day, I remember Dr. Bahati Sinha. She's postdoc, also clinical doctor. She's in the hospital. So very good skill to do HI model for tiny pups. One day she came to me, said, Dr. Wang, you know what? I don't know what happened. I have 3 liters mice today. All after HI treatment, all died. I said, oh, what happened? Normally, if you do experiment, okay, I have 8 or 6 pups in the 1 liter. Maybe die 1, 2 by experiment. Sometimes die less logically, but all died. All died. No one left. See, what happened today? You something wrong? I said, no, regular. something wrong. Something major things wrong. And later we check, okay, that's all mice, MT1 knockout mice. But beginning we don't know MT1 knockout mice, if we do treatment, will be all died. So later on we figure out, okay, that's MT1 knockout mice. And we repeat. We see not only 3 liters, we repeat more liters. Want to like for sure, this is really the case or something wrong. So okay, so later on we show this like about 55 mice. This MT1 pups all died during experiment. Just I try treatment. And here regular mice, during the treatment we have maybe 5 or 6 die. So significant difference. So that means knock out this protein, make mice more sensitive to the dyes, to dyes, like how increased mortality. And we're also working with right now with my lab right now also working with MT1 knockout mice to check more drug. Things are undergoing. Okay, so now I try to say how about situation here for molecular mechanism of melatonin. I should quickly, I say the watch, yeah, already time flying. Okay, so for melatonin molecular mechanism, we focus 2 things. One thing is inhibition, mitochondrial cell death pathway. Another is activate antipoptocytes survival signaling pathway. Here's one scheme from my solo review paper. So I try to document here melatonin. Okay, inhibition, cytochrome C, SMAC, ERF, NOG, also caspase pathway, like caspase 3, 6, 7, to melatonin inhibition this cell death pathway. Also, melatonin also activated anti-apoptocytes survival pathway like AKT, ERK, MEK, and also NF-κB. So here's the table to try summarize. We have bunch of apoptotic mark working with this drug target this kind of mark, apoptotic mark like cytochrome C, SMAC, ERF, MTPTP, also BUX, BAD, ROS, and PRP, caspase 3, NAM1, L1 beta, RAP2. Also not done yet. Also DNA fragment, also tunnel positive cells, junk, PAR4, NF-κB. So next slide shows melatonin active anti-apoptotic survival signaling pathway. Melatonin target PR3K, AKT, BCL2, BCLXL, junk, ERK, and RAF1, MEK, NF-κB. I summarize not only for SDROG, but SDROG is the major thing I want to talk about today. And we also summarize with AD, PD, Huntington, ALS. So here's an example. Melatonin is an inhibitor of cytochrome C release, block to the melatonin function. You can see here, this Western blot shows if you put cell in a apoptotic condition, cytochrome C release from cytosolic. You see the band higher, the band here. If you put melatonin, band disappear. If you give leucine, again, the band appear. So also caspase 3 show similar things. Like cleavage caspase 3 here about 17%, 17 kilodalton doing. Here's pro caspase 3, 32 kilodalton doing. And here you say apoptotic cells have more cleavage caspase 3, active caspase 3, but melatonin have less. Leucine gets things back. Okay, so conclusion is MT1 agonist melatonin mediated neuroprotection through inhibition cell death pathway, all active survival pathway in the stroke model requires MT1 receptor. Okay, now we think we show data works for melatonin. How about other MT1 agonists? They have bunch of drug there. So far we have 146 MT1 agonists already documented from G protein COPT receptor PCR legend, like this is a database. They have one common things. They have in the core skeleton, the structure, have same things. And here's common used 18 MT1 agonist. I will be focused, like today I already talked melatonin, another is N-acetylserotonin called NAS. NAS is immediately precursor for melatonin. Both have, as I said, both have core skeleton. And so this is both drug have common things. This is both drug, they are MT1 agonists. They are NINDS, NIH-NIDS, 1,040 compounds. Both are antioxidant and both anti-aging. And is director, this is like a supplemental things. The material you can, this one melatonin you can buy from CVS, but NAS I didn't find from NAS. People talk like from banana you have more NAS. But anyway, so okay, different things for the two drugs. NAS is better antioxidant, and NAS have wider distribution. Here's NAS in the MCO model, and we show as melatonin data, we show TTC. Here we show if the MCO mice with NAS treatment, we get protection. We get protection by post-treatment, and here's pre-treatment. So here's like a vehicle. This is the drug. Vehicle, it's drug. This is quantitative data. And we published this paper from last year, I think, it's Journal of Neuroscience. Here's we have organic typical hippocampus slice culture. This is slice culture. You cut like a brain is left culture. You culture in the hood. They can survive like 1 week, 2 weeks with no problem. So we did propidium iodide staining. All staining cell is apoptotic cell. So this is control cells. It's like kind of background. Control slide background. But if you put with OGD treatment, you see more killing there. This is lower magnification. This is higher magnification. If you put drug with NAS, you have less killing. So the NAS works for animal MCO whole mouse, also works for the small pieces of organic typical cultures. And we also have data shows NAS works for cell cultures. I didn't show here. So we want to focus, okay, how about NAS mechanism? We focus two things. One thing is this drug will be inhibition mitochondrial cell death pathway, similar with melatonin did. But this drug also did for the autophagy cell death pathway, inhibition this cell death pathway. This data shows LCMS data. We try to confirm with people, also confirm with ourselves. If a drug, we do IP injection, people will be asked, if you do IP injection, how about this drug pass BBB? If not pass BBB, how you can say the drug have function because you put this drug? So let's say, so we did NAS determination in brain of mice with ischemia injury. We use LCMS. Here's standard control. We have the count, how many count by this machine. It's 18268. This is like a positive control. This is blank control, like a negative control. This one is with mice with MCO without any drug, like endogenous NAS. How many? Yes, with ischemia, you're right, with ischemia. So this we get count 4232. But if you put drug and with ischemia, this is the number. So a lot of drug already past BBB into the brain area. Okay, and here the data shows NAS release cytochrome C. This is cytochrome C after MCO, they get a lot of release. very strong release comparison with regular mice. And here with drug, NAS treated, get pretty like a significant difference, reduce cytochrome C release. This caspase 3, we show this data, NAS decrease caspase 3 activation in the MCO mice. And this figure shows how about culture data. So this is PCN cell culture data. We show NAS offer neuroprotection through inhibition mitochondria fragmentation in PCNs. We use TOM20 to do immunostaining. Then we count how much the size. So we get document, yeah. And this one shows NAS offers neuroprotection through inhibition autophagic cell death pathway in several models of stroke. So let's see here. We treat PCN cells with 2 hours H2O2 apoptotic induced, also with 18 hours H2O2 treatment. You see here LC32, the second band, not first band, not LC31. This is 2, this one. You see very strong band here appear by H2O2 treatment. And you put NAS, band almost gone, only a little bit there. So significant difference. And here Backlin 1 also we got increase, and P62 got decrease. And drug changed the autophagic cell death. And this ones we try to staining the cells by MDC, is specific mark for autophagy. We also call like autophagism. You can see here the small like this autophagism, the small dots like here. So this H2O2 treated cells comparison with control, so a lot of staining MDC. You put NAS, getting better. Here is 18 hours, small dots there, and with drug get better. So we think NAS working for inhibition autophagy cell death pathway. This one is from in vivo data. We already show in the cell culture in vitro, but this one's in vivo. This one is in vivo. Okay, my time's coming. Okay, so this is the LC32, similar thing with cell culture. It's the MCO model, and this is Backlin 1, this P62. Okay, so both models works show this NAS, this drug working for inhibition autophagy cell death pathway. I try to finish up my talk today. So try to thanks for NIH and NDS support my lab work, and also Bill Gates Foundation and MDA, LS Typical Company, and Prize4 Lab Company, also HDF. And here's Harvard Medical School. I got one picture there. And try to thanks for my lab member, Hannah Bahati. She's the person that anti-1 knockout mice pop story. So Dr. Jane, Simon, David, also Anna, and Rachna, and others. Here's my collaborator from Harvard Medical School, Dr. Chris Bruce, and Irina, and also Mary Kudwaz, Dr. Joe, and Rose Du. And other collaboration internationally, here is still United States, University of Pittsburgh, Robert Freelander, and Lily Moore from Canada, and Dr. Zhang from FDA, and also Dr. Zheng from University of Toronto, Canada, and one collaborator from China, Wuhan University, Dr. Li Ming Chang. And everybody is my lab people who have a happy stock meeting. Yeah, it's done. Thank you. Thank you. Thank you. So any questions? Okay, go ahead. Yeah.
Thanks very much for a very good talk, indeed. I wanted to ask about the NAS and anti-aging effects. So are the anti-aging effects, they primarily through autophagy, or do you know if molecules like sirtuins are involved, or some other of the longevity type pathways. I notice you mentioned with autophagy, it's a separate question really, but do you look at, I guess do you look at all the autophagy markers, sort of Becklin and so on? Yeah. So I just wonder if sirtuins are involved.
Okay.
Certs and different certs, yeah.
Okay. Thanks for the next question. Excellent. So for aging, yes, I personally did aging research for my PhD from Jerusalem. So I'm personally pretty interested for aging story. This melatonin works, people talking, oh, this drug is anti-aging. So I have many publications. So my lab was thinking like using melatonin to be the drug for the neurodegeneration disease model, like mice, like AD mice, or even ALS, they're like, AD is better, they have a long life, to show how about melatonin works for anti-aging. But we still not get like very strong data to show this very beginning, yeah. And another question you said, like a apoptic mark. We did a lot of apoptic mark to test, yeah.
And molecular markers for autophagy, which are the main markers you look at?
Well, that one, I think LC32, we did.
Thank you. Thank you.
Yeah. Okay, go ahead. Yeah. Okay. Yeah, almost.
Yeah.
Oh, okay. Yeah. Okay.
So I saw that you like hydrogen peroxide in your model to induce the cells death, and they are showing us that melatonin and acetyl serotonin is inhibiting. So my question is, did you try in your model to use the enzyme which scavenge hydrogen peroxide? We know that, okay? Mm-hmm. To support, those effects of melatonin, or you are not using that? This will be not the way how you can support maybe those effects, okay?
Yeah, that's a very great idea. I know. This is much better. I mean, this is like a confirm H2O2 treatment, but we thinking that we didn't try yet. I think after back Harvard, I should do that. Yeah, so like more confidence for the support my data. Yeah, okay.